Good morning. Today we will discuss a new topic from the paper CHO 350 organic reaction mechanism. And from this we are going to discuss about free radicals, how they are generated, their stability, their reactivity, and further topics in free radical reaction. In this free radical reaction mechanism, we have to think about free radical reactions. And what is free radical also? That is a question. Free radical is any species which contains single electron. It's called as radical or free radical. Any species may be based of nitrogen compound, carbon compound, single hydrogen, oxygen, hydrogen atoms. So any compound which contains single electron is called as free radical. How free radicals are formed, or simply how radicals are formed, it is formed by breakage of bond by homolysis. What is homolysis? When a bond going to break equally between the two atoms. Such bonds are called as such breakage is called as homolysis. Okay. To understand this homolysis, we will take example. So see, see here. This is the molecule having A and B elements connected by a bond, and this arrow showing that half-headed arrow, the half-headed arrow showing the breakage of this bond equally. So this A will carry one electron, B will carry electron, and this reaction takes place in the presence of light, sunlight, or high temperature. So these two radicals are formed. These two radicals, A dot and B dot. These two are called as free radicals. What about the stability of free radicals? Free radical stability is nothing, it is directly proportional to or it is similar to carbocation stability. What we know about carbocation? What we know about carbocation stability? We know that tertiary carbocation is more stable than secondary carbocation, which is more stable than tertiary carbocation. Similarly, we can say tertiary free radical or like this carbon is more stable than secondary free radical, which is more stable than 1 degree or primary free radical. Primary free radical, C carbon, which is more stable than methyl radical. Okay, similar to carbocation. What we have seen for carbocation, similar for similar pattern of stability is observed in the free radical. Fine. Next point is how some examples undergoing free radical reaction. See here, this is the triphenyl. This is what chlorotriphenyl methane. This carbon having the three phenyl groups here, here, here. So when you heat it in benzene, CCl bond become weak and breakage takes place. And it forms Cl radical here. Cl radical will also form, and this radical will also form. That Cl may combine with Cl and form chlorine gas. This radical combine with another radical and dimerization takes place. It's a dimer formation. Okay. So it is a simple reaction we have seen in which the free radical formation takes place. These free radicals undergo into dimerization. So you can see here. Fine. There are many reactions, but there are certain conditions. This dimer formation takes place when there is no air. If air is there, then this dimer, this radical will combine with air, means there is oxygen, and oxygen also form bond with this radical. So radicals are highly reactive. They can react with any reactant, even air also they can. Why? Because in air there is a presence of water molecules and oxygen molecules, and therefore these radicals randomly react with them. Okay. See, this this triphenyl methyl chloride, triphenyl methyl chloride, which is considered as a wine red color, that becomes yellow solid when you react with heat it with the presence of benzene, indicating that there is a formation of free radicals, and which after a certain time, after time interval, that becomes really become white solid, indicating that dimerization takes place. So having the observation about color changes, free radical reactions can also be judged. Many reactions we have seen, we might have observed that in photochemistry based reaction can be observed by changes in color taking place from reactant to product formation. If there is a air, if we are hitting this triphenyl methyl chloride in benzene and in presence of air, so they will form peroxide line. Means the insertion of oxygen takes place. And because oxygen is highly reactive, what is the reason of oxygen is highly reactive? Because oxygen is paramagnetic in nature. Oxygen is paramagnetic in nature. Therefore, it easily reacts with many types of reactive species. Okay. So now look at the stability of this triphenyl methyl radical. So you will find that it's the highly stable or most stable free radical. What is the reason? Reason is very simple. This radical undergoing into resonance with this phenyl ring at this site. So this phenyl will provide total conjugation or delocalization of electron. After that, this electron can involve this side of ring, and it can rotate, it can delocalize and provide give extra stability to the radical. And from this side also, this may also undergo into what delocalization, or we can say resonance, and therefore three phenyl ring stabilizing this radical. Therefore, it is considered that triphenyl methyl radical is a highly stable radical. Is a highly stable radical. Fine. So now, next point is about depending upon the stability of the free radical, we can measure the rate of reaction in which dissociation takes place, therefore called as dissociation constant. See, before you, there are three examples. Three compounds are given. You look at C first of all. What is this? It is the ethane. It is the ethane. When ethane, when ethane, when ethane undergoing dissociation means breakage of one carbon and one hydrogen bond, that will give you a certain radical by homolysis. In the next B example, we have replaced all three hydrogens by three methyl group. You see, these two carbons are there, carbon single bond carbon. These three hydrogens are replaced by three methyl groups, one methyl here, 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 right? Like that. And and this side also, we have replaced these three hydrogens by three methyl group, one methyl, second methyl, three. And in this A, instead of methyl, we have used a phenyl ring, phenyl, 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 and here also at this carbon, phenyl, phenyl, phenyl. So there are three compounds before us, and our aim is to heat this compound, or our aim is to expose this compound to the light, sunlight, in order to bring out the homolysis or homolytic fission in the compound, and to know about these reactions, this compound which is having the fast rate. What is the dissociation constant? It is a rate constant. It is nothing but equal to rate constant. What is the rate constant? The reaction at which, the reaction at which, the reaction at which, the reaction at which the reaction is taking place, or reactants are converted into the products. And that is always in terms of concentration divided by time. That is called as rate of reaction. So dissociation constant is nothing but similar to the rate constant. So if you imagine now these three reactants, these are three reactants A, B, C reactants. So if you imagine these reactants A, B, C, this C undergoing homolysis, one C and this H bond breaking, or consider CC bond breakage. So if you consider CC bond breakage, CC bond breakage, CC bond breakage. Okay, so we are observing three reactions separately. So this on homolysis will produce methyl radical. Fine. This on reaction produce trimethyl methane, or we can say tertiary butyl radical, and this will produce triphenyl methyl free radical. So most stable would be which one? Which is forming from the, yes, which is forming from, which is yes, which is forming from A, right? Yes, this would be 100% stable. The reason is, this reason is what? In this free radical,
Stability of carbocation in with the resonance of phenyl group.
yes, so we can say because three phenyl are there which are stabilizing this radical, and therefore we can say the dissociation constant will be higher for A compared to B and C. And which is having the least one dissociation constant? This C. C definitely would have the least dissociation constant. See, this is the radical before you, okay, which is having one hydrogen on the carbon and two substituted ring. Okay. So, but if you see, there is a too much crowding on the ring. You see, methyl are there, methyl are there. So, see, it's a very important example again. See, we are trying to or react this it's a complete reaction. This carbon carbon bond easily break undergoing breakage. Why? The reason is because of this carbon become highly crowded, right? This carbon become highly crowded. This carbon also become highly crowded. Therefore, this bond break by homolysis. This bond break by homolysis like this, and radical will form. So this radical is this one, and it is found to be most stable radical. What is the reason? Reason is very simple, because this is this is the more stable compared to this molecule, because in the molecule, due to the uh, exhausted or very much crowding by this phenyl ring, that bond undergoing breakage, and you get the free radical. So actually this is like this. And one example is another example. So similar, this is the molecule which is highly unstable because of crowding of this ring. So this bond become much more strained bond. That bond works under pressure, we can say, or that bond become very loose, very weak. Why? Because of continuous strain pressure from the bulky groups on this carbon. Therefore, this bond will try to undergo breakage. This bond will try to undergo breakage by homolysis, and this homolysis takes place, and there is a formation of this radical. This radical is stable compared to this molecule. The reason is, in this radical, steric crowding is less, or compared to this is very less. So this is the one of the factor. What is the factor? Steric crowding in the molecule may also lead for the formation of free radicals. Okay. Fine. Next is what? See, this is the another example before you. You might have seen hydrazine. If you see hydrazine, this is the hydrazine, hydrogen, 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 hydrogen. This is the hydrogen. Hydrogen actually is a gas. It's gaseous in nature. Hydrogen is the gaseous in nature. What happened to hydrogen? These hydrogens, if replaced by phenyl ring, this is also by phenyl ring. This is also by phenyl ring. This hydrogen we have replaced also by the phenyl ring. So what happened here? You see, when they replace this, that, that hydrogen nitrogen nitrogen bond means this bond become sterically crowded or strained bond. Same thing. So undergoing to homolysis, this bond undergo homolysis and formation of radical. This radical is also more stable. What is the reason of stability? Delocalization is the reason. This electron may involve in resonance, and it rotates throughout the ring and again come back, then involve here this side, and passing through all centers in benzene, again coming back, and this process continues, and this provide extra stability to this particular radical. So hydrogens, remember hydrogens are those compounds in which nitrogen single bond is present. This single bond indicate within the nitrogen, the given compound is hydrogen. The given compound is hydrogen. Right. So another point is generation of free radicals. How the free radicals can be generated. Today we will see there are actually many methods by which free radicals are generated. So one of them is peroxide cleavage. So what is a peroxide? We know what are the peroxides. Having the oxygen single bond. What is the hydrazine? We know the hydrazine. Having the nitrogen single bond. Azo compound. What is azo compound? Having nitrogen double bond. So be clear with this. Oxygen double bond. Oxygen double bond. Oxygen double bond. Single bond, not double bond, is a peroxide. Nitrogen single bond is a hydrazine. Just now we have seen the last slides. Nitrogen double bond, azo compound. So be clear with this, azo compound. Azo means compound means nitrogen double bond containing compounds are called as azo compounds. So peroxide from peroxides means oxygen single bond, and there will be some other groups. So these such compounds are called as peroxide. When nitrogen single bond and some other groups are present, this is called as hydrazine. When nitrogen double bond, when nitrogen double bond and some other group, this is called as azo compound. Okay, fine. So these are the azo compounds. So from this we can prepare the free radicals. Okay, we can prepare the free radicals. So few of the methods we have mentioned here. By using these methods, we can generate peroxides. We can easily generate peroxides. Let us go discuss one by one. From peroxide, using peroxide cleavage, using peroxide cleavage, undergoing the homolysis, and that will give you the free radicals. And we should know the definition of peroxide also. If you know the definition of peroxide, we can easily find out the product containing free radical. So this oxygen bond, when undergoing heat absorption in the presence of sunlight, HNU. HNU is nothing but the sunlight. Okay, HNU is nothing but sunlight. This bond cleavage takes place. This free radical, the reactive free radicals, very reactive free radicals formation takes place. So now, see, this is the generation of free radical from peroxide. Okay, example is before you. This benzoyl peroxide is a highly valuable, most important chemical or peroxide we use in the organic chemistry. This for benzoyl peroxide is also called as initiator in many free radical reactions involving the coupling reactions or combination reactions. This benzoyl peroxide is widely used in the polymer chemistry as a chain initiator. How it will react? This benzoyl peroxide, first of all, undergo heating, on heating, undergo homolysis. This bond undergo into homolysis. This free radical formation takes place. This free radical formation takes place. This is the benzoyl free radicals, we can say, or benzoate free radicals. In fact, it's a benzoate free radical. We can call this as a benzoate free radical. So it is a benzoate free radical. Benzoate free radical. Okay. It's a benzoate free radical. This benzoate free radical, again, this bond, this carbon, phenyl carbon and this carbon undergo again homolysis. This undergo homolysis, and this again form another molecule which is a living group carbon dioxide and phenyl radical formation. This phenyl radical now interacts with the other reactants in the reaction, and it propagates the chain, called a chain propagation reaction. So here benzoic peroxide undergo homolytic cleavage, and it form such free radicals. Another example is tertiary butyl peroxide. So similar fate would be observed for this particular reactant. For this reagent, or we can say peroxide, tertiary butyl peroxide, if you provide the heat or sunlight, this oxygen-oxygen linkage undergo bond breakage, and after the bond breakage, it will form reactive free radicals. This is this. Okay, fine. So another method by which we can prepare the free radical is from Azure compounds. If you will take Azure compounds, what are the Azure compounds? We know those compounds containing nitrogen double bond. So in Azure compounds, actually what happens? These two bonds undergo homolysis. This bond homolysis and this bond homolysis. And this we know that when one bond break, two electrons will form. So this one bond will give one electron to this R. This one bond electron, this 2R will form 2R, 1R, 2R. And electron on this nitrogen from this bond break nitrogen, that from double bond. So one pi bond. So we can say this N2 is nothing but it contains nitrogen triple bond. Nitrogen triple. Okay, right. So these are the examples which involve the formation of free radicals from Azure compounds. See, one more example is before you. Tertiary butyl group is attached to Azure compounds. This is Azure functionality. This will also undergo homolysis. How? This bond undergoing homolysis. This bond also undergoing homolysis, and this tertiary butyl radical will form, and nitrogen gas also evolve in this reaction. Okay. So this Azure compounds we can say undergo into homolytic cleavage, and they form the variety of compounds or variety of free radicals. Okay. So you got it? Yes, 2R. Here 2R will form. We can say here 2R will form because this molecule contains two. Similarly, this two alkyl part, one alkyl part and one alkyl part. So this will form this. So hope all of you understand this, how the free radical formation takes. One more example is before you. Similar fate would be observed for this given compound, irrespective of the complexity in the molecule. Our aim is to focus only the bond the bond. Which bond? This bond. This bond. Focus this bond. Focus this bond. Why this bond? Only because our aim is to remove nitrogen from the molecule. This nitrogen removal is our aim. So this bond undergo homolysis. This bond undergo homolysis. This bond undergo homolysis. And there is a formation of a generation of free radical like this, and net into gas evolution takes place. So any compounds which if you find azo compounds, and if you are hitting such compounds, so you will find that this such compound shows removal of or elimination of N2 gas, generation of free radicals. These free radicals can combine with other reactants in the reaction and they yield different products. Okay. So next point, what is next point?